It's my pleasure to introduce a friend and colleague of mine, Dr. Pleil, who's both a mathematician and a physics person, as well as an engineer. You have a combination of all of those degrees in your pedigree. Dr. Pleil originally worked for Northrop Corporation as a senior scientist designing laser-based optical instrumentation. And then in 1987, he moved to the EPA, where he's been a senior research scientist developing analytical methods for measuring organic environmental pollutants. Over the past 10 years, he's been a subject matter expert for the U.S. government in human biomarker research. He's published over 100 publications. He also serves as a professor, an adjunct professor at the University of North Carolina School of Public Health, and he mentors graduate students through that system. He's a founding member of the International Association of Breath Research, and something that I didn't know existed until I saw this bio, the Submarine Air Monitoring and Purification Organization. I guess that makes sense that there would be one. He also serves on the editorial board of Biomarkers and is the editor-in-chief of the Institute of Physics' Journal of Breath Research. So it's my great pleasure to have Dr. Pleil here to talk to us today.
How do I advance? Oh. Hi there, how are you? Glad you all showed up today. I'm going to give you a kind of overview-ish talk about a lot of different things that we do at EPA, and I'm going to try to focus on 1, 2, or 3 subjects, time permitting, and I'm going to gauge how many people fall asleep. So, that said, I work for EPA. And I'm on the side of trying to figure out what an exposure does to you until you're about ready to get a disease. And then I work with people who then pick it up from there and take it forward to the adverse health outcome. So, we call this exposure science. We measure contaminants in environmental media, air, water, etc. We also measure things in blood, breath, urine, and we try to link them all together so that we can hopefully try to mitigate the adverse outcomes from chemical stressors and other stressors in the environment on human health. So what I'm going to try to do today is look at a few different examples of legacy and new EPA research and where exposure science plays an important role. But before I start, I figure most of you don't even know what EPA really does, and so I'm going to talk a little bit about what we do, how we're structured, at least on the Office of Research and Development side. As you know, EPA is primarily a regulatory agency. I don't do any of that. I'm a pure science guy buried in the bowels of one of the biggest EPA research labs, in fact, the biggest EPA research lab in Research Triangle Park, North Carolina. So before I start, all these guys here are some members, current and legacy members who have stomped through my labs and whose fingerprints are on the things I'm going to talk about today. Many of them are now moved on to new jobs. I don't have pictures of the new guys yet because they haven't done anything yet. Their pictures will come up here when they do something. So, I have a few colleagues at EPA who are very instrumental in the work I'm going to talk about. The guy on the left, Mike Madden, Jane knows, is a wonderful guy. He's my counterpart on the health effects lab. I'm on the exposure lab. The guy in the middle, Bob, he's no longer with the agency, but at the time a lot of this work was done, he was my IRB person. We have our own medical staff to do IRB, that's institutional review, for our human studies. And the guy on the right, Andy, he's a current colleague right now. We co-publish, and he runs our medical staff for the human subjects. He does all the medical stuff you need in order to get healthy adults into an observational study. And he's also quite the expert on iron metabolism in humans. Matt Wolfgang, who Jane knows, is a researcher at UNC that I've worked with, and Sarah, who I had to add the doctor to. She just graduated. We worked on CF, cystic fibrosis, and exhale breath together. My guys from University of Pisa, two of the people in that picture got their PhDs in part by working in my lab. And the guy with his kind of side to us is Fabio Di Francesco, who's their boss. And I've been over there maybe 8 or 10 times, and some of their people have spent time in my lab. My main guy, John, okay? He keeps me honest. We have the dubious distinction of having been the oldest and youngest PhD students in Steve Rappaport's lab, sharing an office as well. And he's now a full EPA employee. He's my go-to guy for all things mathematical having to do with mixed modeling and variance structures of data and other things too. All right. So in addition to doing internal things at EPA, I work with a lot of different people all over the world and have for the last 25 years, doing everything from dealing with the military on certain areas, the three-letter agencies, which CIA, FBI, those kind of guys, NSA, and also a whole variety of universities. So when you work for the government, you're often lent out to other entities, or you collaborate with other entities on various subjects. The agency itself, we have a boss named Gina, and we have lots and lots of boxes because we are an agency. About 80% of the agency is regulatory, and the other 20% is science. And as usual, the science guys eat up 80% of the budget, okay, because labs are expensive. I work in the Office of Research Development, which is called out there. We have about 2,000 federal employees. And within the Office of Research and Development, we have a series of laboratories. I work in the National Exposure Research Laboratory. We have about 400 feds and about 250 or 240 contractors. And underneath that, we have a bunch of divisions, and I work in one of the divisions where we have about 100 feds and 140 contractors. We're the biggest division in the Office of Research and Development. We're spread out all over the country. The ORD, Office of Research and Development Labs, have multiple locations, and they're pretty much spread out based on what kinds of environmental issues are dealt with. The biggest one, of course, is RTP, where I work, and we basically advise the states and regions. So we have a regional system. We have 10 regions, and these are the guys that each region has a lab, but they do enforcement action, and we then advise them and give them methodologies to make the measurements that it takes to be able to enforce regulations and law. So at RTP, we have 3 main EPA research labs: the National Exposure Research Lab, where I work, the National Health and Environmental Effects Lab, where Mike works, and then we have the NERML guys, who are more your people, I guess. We call that our engineering lab. They do everything from scale up to whole factories and emissions, and they have houses that they monitor for air infiltration. They do all the big stuff. The R and the M actually stand for risk management, but the bottom line is those are our engineering guys. Big stuff. This is an aerial shot of the EPA campus at RTP. We have about 5,000 employees here, of which about 2,000 are contractors. We also house the computational facility, the CompTox Center, and we also run a whole bunch of big computers there, and we do all kinds of things there for other agencies. And we, for many years, ran all the weather models for the National Weather Service. We still do all the ozone models, the PM models, computational toxicology, et cetera. So that building's just full of computers and things, and little squirrely guys who run them. This is just what it looks like there. Behind me, when I took this picture, is the NIEHS facility, which is one of the Institutes of Health. And And this is just the building that I work in from the front. We also have a building on the campus of University of North Carolina, and this is where we do our human health studies. It's called, interestingly enough, the Human Studies Facility, where we have our own clinic, our doctors, our nurses, and then we also have a whole suite of environmental exposure chambers which are unrivaled in the world. We have exposure chambers that people can live in for a week at a time, all the way down to ones that are about the size of you, like the size of a phone booth. And we can do all our own exposures, our clinical medical studies on health effects of ambient air pollutants. All of the national regulations for ozone and particulate matter, the science came out of this building. Okay? This is the place where regulations come to die. No, where regulations are created from our human studies. I also, like Jane said, I'm a professor at the University of North Carolina School of Public Health, and this is just some pictures. UNC, you gotta root for your school and all. So our facility is pretty big. It's one of the biggest schools of public health in the country. We have 3 buildings that are now attached to each other. And, we basically run $1 billion worth of research through there. By the way, one of our med school guys just got the Nobel Prize for DNA repair. But that's not in the School of Public Health. They're across the street. But we take credit for them anyway. I work in this building called the McGavran-Greenberg building, and my office is somewhere over on the right. So that much for the boilerplate about EPA and what it looks like. It's a nice place, so if you guys are looking for postdocs or maybe a faculty appointment, this is not a bad place to look. We're considered to be the best place in the country for a postdoc to work. It's mostly because we pay more than anybody else. We hire our postdocs in as GS-12s, so it's a pretty good gig. It's about double what NIH pays. Anyway, so now let's do some real work. Exposure science. Okay, we used to call it exposure assessment, and somebody thought that wasn't sexy enough, and so we changed all our acronyms to use S instead of A, including the association, which used to be ICEA, and then we cleverly changed it to ISIS. That was before the other ISIS, okay? So it wasn't really our fault, but we substituted the A with an S. And that same thing is true for the journal. So anyway, it is what it is. Just thought I'd mention that. In case you run into ISIS, it's with an ES at the end for exposure science. All right. So the thing that we do in exposure science that we've kind of been driven to is because of the genetics guys. Okay? We have now realized we got to heavily worry about the gene-environment interaction ever since they sequenced the human genome. Because, as you all know, that's really complicated. Now imagine laying exposure on top of that, okay? Making it really messy. So we've kind of approached this from a systems biology standpoint. And we're having to get away from this one compound, one deadly disease kind of paradigm. So how do we do that? Well, we make lots and lots of graphs and figures and flow diagrams. This particular one is one of my personal favorites, where we have fully realized, in human especially, there's some things we can measure and some things we can't measure. Okay? Oopsie. Oops, bad move. All right. So, the things we can't really measure are like how many scoops of benzene are in your brain, or that kind of thing. You can do it with rats, but you can't do it with people. All right? So those things we have to model, and we represent those with the triangles, and we're going left to right from exposure to health outcome. The things we can measure are in the blue boxes. Okay? Here we don't have to take the people apart. We can certainly measure what's in your environment around you. We can certainly measure biomarkers, which are chemicals from the outside that are now living inside, get an estimate of dose. And we can measure what we call effects biomarkers that I call preclinical markers. People have different words for some of these things. But those are things we can measure that could be an endogenous response like a cytokine, or it could be benzene oxide, or something that incorporates the original chemical but is now changed. But as you go from left to right, you get closer and closer to the health outcome from the exposure. And then in the middle, this is where the really important models live, where we actually link something we've measured to something that we are approximating. Okay? So you kind of get the idea of how we're looking at this. And many of these pictures were drawn by my very good friend John, who is really good at making pictures and figuring things out for me. Oopsie. All right. This is kind of where I live, where the big star is. Yes, I do environmental measurements, and yes, I delve into the effects measurements, but the bread and butter, the reason they pay me is for that, where the star lives, okay? Yeah, and I play some math games, and I'm pretty eclectic, but that's what I really do. So, question is, why is this important? Well, as a federal agency, we get told what to do by other people. People like the National Academy of Sciences, Congress, etc. In all of the recent tomes put out by the federal government and people who advise the federal government, the one common theme has been more biomarker data, making it, and also using biomarker data that already exists for what? For risk assessment, for risk management, okay? Well, we've been fooling around with this a little bit. The good news is there is a lot of biomarker data out there. There's something by CDC called the NHANES study, where they measure everything that lives in people, 5,000 at a time, every year or two. They publish it, and you can now data mine this. The kind of downside is most of the data is metals. Doesn't help me much, although there are data to be mined there. So that said, our guidance is to use existing data, make more data, and infer the exposure to health outcome pathways. Okay. So there are some general topics in systems biology research that I deal with. Integrating environmental and human biomonitoring data, worrying about the genome-exposome interaction. By the way, does anybody here know what the exposome is? It's pretty much anything that's not the genome, okay? There are lots of definitions, but basically it's the chemicals in you that are not the genome. Kind of leaves it wide open for interpretation. And in every paper you read, there'll be a slightly different definition. One of the new approaches that we're using now is what we call top-down or discovery or non-targeted analysis, depending on which paper you read and from which group it's from. The idea is, rather than picking on an individual thing that you're worried about from the environment, you try to discover as much as possible as you can from a sample and then figure out what might have been from the environment and if it had any value. Top-down is something that is an academic phrase. We call it non-targeted or discovery analysis. We want to interpret the data that's already existing, as, for example, in NHANES, but there's also Germany HANES and Korea HANES. They don't really call them that, but I call them that. So different countries are also providing databases of various biomarker research that they've done. And finally, our newest thing is something we call adverse outcome pathway. And I will talk a little bit more about that later, but the general gist is figuring out something bad that happens in an intact human and see if we can reproduce it in vitro to speed up our toxicity testing and yet be relevant still to the systemic biology. I play a lot with mathematics and statistical data interpretation. One of my personal favorite things is data visualization because I often have to explain complex data results to people who really don't care about numbers but just want to get the overall view. I call it explaining stuff to the boss. The other thing we look very carefully at is variable independence and clustering of variables to gauge non-independence. We run a lot of stochastic models. We worry a lot about metadata, and certainly we worry a lot about longitudinal data. This is like before and after kind of things. So the interesting thing about working in this regime is we get to play with a lot of different things. So I've been involved in World Trade Center. It's a transient event. It's a longitudinal kind of study. I'm currently working with NIOSH on firefighter exposure during firefighting. Spent 5 years working with the military on jet fuel exposure. Spent a year and a half working on the F-22 debacle, where we lost a couple of airplanes due to the human engineering interaction during G-force and oxygen provision at altitude. I've been working for a number of years now with NASA on space shuttle, space station, and with the submarine community, like we mentioned before. I'm one of the legacy members of SAMAP, Submarine Air Monitoring, Air Purification. These are all places where if you have a problem, you can't open the window. Okay? Think about it. And so it behooves us to know something about the environment before we have a problem. So we've been working with what I call discovery analysis, which is taking a look, not just what happens in the environment, but also what is already inside the person and going in both directions to the population in between. The other thing we're dealing with very closely now is the in vitro to in vivo linkage. And you can see in the lower right-hand corner that when we run human studies and animal studies, we have a lot of relevance to humans, a lot of cost and complexity, but very low throughput. If we go more towards the molecular side, we have lots of throughput. It's pretty simple, but our relevance to human toxicology and human systems biology is depleted. So neither one is bad, neither one is good. It is what it is. If we want to do it fast, we have a relevance problem. If we want to do it relevant, we have a throughput problem. Work a lot with data distributions and data interpretation. Most of what we do, our hardcore data, tends to be log normally distributed. This is an oft overlooked feature of biological and environmental data, and it's done wrong often in the literature. So I've been harping on that for a number of years now. Work a lot with data visualization using heat mapping, which we stole fair and square from the genomics guys. And this is the chemical prioritization. This is actually John Sobis' slide. What we're trying to do now is make data visualizations for individual compounds, and we're making these little Pac-Man figures so that with a single glimpse you can see things like how toxic is it, how prevalent is it in the environment, and what was the other thing? Oh yeah, and how likely you are to get it into your body. Okay? So we just had a workshop on that at EPA, and it was very successful. So I'm going to touch on a few specific topics, and I'm going to quit with these as soon as I run out of time. Okay? I have lots of info. By the way, I teach a class on all this, so I've been doing it for, 8 or 9 years. I have lots of material. It kind of had to pick and choose a little bit. So one of the things I pointed out, and I figured since you're an engineering crowd, you might be interested in a little bit of the math that we have to deal with. And One of the problems I run into a lot is I'll do a study and I want to put it in context with other studies. So what I want to do right now is to convince you that pretty much anything we do in the lab that has to do with people or the environment is most likely log normal. And, you know, a lot of what you do in an engineering lab might be perfectly normally distributed because you don't have external factors. But for us, we have lots of external factors. And so we can possibly have really big numbers, but we can never have anything lower than zero, right? I mean, what's a negative benzene? Got nothing there for you. I want to show you that the literature makes this hard to do, and I'm going to show you how we got around that and how we can then apply this to interpreting the big databases, which is one of the missions we have from Congress. So in doing this, John and I actually built something we call our ICC risk tool, ICC standing for interclass correlation, where we can try to predict means exposures, distributions from cross-sectional exposures from spot measures where there's no repeat analysis. This is really important because here's how we look at life from a toxicity and environmental standpoint. Toxicity is pretty easily measured by dosing rats and cells and whatever. You can say this stuff is more toxic than that stuff. The question is, how likely are you to encounter it in the environment? And so if this stuff here, whatever it is at this level and it's toxic at this level, what are the chances of it being a problem? Pretty slim. On the other hand, if you encounter it in the environment here and it's toxic here, now you're starting to have overlap. So we need to know these things in order to be able to interpret cross-sectional data from toxicity with respect to cross-sectional data from exposome measurements or biomonitoring measurements. So this is what, and this is probably below you guys, but this is how I'd explain it to my students. I said, suppose you make measurements and they're all equally likely. Okay, so in this case, we're rolling 2,000 dice, and you know we can get a 1, a 2, or 3, a 4, or 5, or a 6, right? And it's all pretty much, you know, equal, right? Here we would use a linear model for predicting what happens. Suppose we take 4 dice and roll them 2,000 times, and each time we add the numbers together, we're going to get something that looks like a Gaussian distribution. Getting 4 1s or getting 4 6s is a lot less likely than getting a 3, a 4, a 3, a 4, a 4, a 3, a 3, a 3. You know, you get the idea. Okay, this is how I explain it to my students. It takes a lot longer because I figure you guys would pick this up real quick. Now suppose we take, and this would be a Gaussian model, right? We can write an equation for that, and we can model that. Okay, now suppose we take the same bunch of dice, and each time we multiply the numbers together. We will get something that looks like a log normal distribution. The log normal distribution is also called the multiplicative distribution in some circles. And here, we model it with a log normal equation. Okay? So let's think about this. If we have biological data or environmental data, we know pretty much it's probably not going to be a linear model. But we have this terrible kind of idea that we should go Gaussian, mean standard deviation, game over. Well, if we use a Gaussian model or a log normal model and a truly linear model, then of course we get garbage, right? If we use a log normal model and a normal model on truly normally distributed data, it doesn't much matter. Okay? This is a good point. You don't really make a mistake by using a log normal model on a normally distributed data set, especially when there's error involved, because you get pretty much the same result. Here's where it messes up. And this is what's in like 80% of the literature. People give you means and standard deviations, which assumes a normal model. And if it's log normally distributed, you get the red model for the blue data. Not a good idea. What happens here? You're going to completely underestimate what happens near zero. You're going to allow 40, in this case, 40% of your data to actually model as negative, which we know doesn't happen. So here's my point that I make to my students is, you got to be careful when you use means and standard deviations for things that may not be normally distributed, because all of your statistical analysis will be wrong.
Are we allowed interruptions?
Well, yeah.
So aren't there other distributions that have...
Absolutely.
Like a Bible distribution? Is
Sure. There's lots and lots of different distributions possible.
Is there a physical argument like chemicals multiply their badness inside?
I'm getting to that. In fact, look at the last line there, right? Yeah, there's lots of different distributions possible. However, if you get a bimodal, that means you're mixing two things together that aren't in the same distribution. The only thing we ever see is bimodal. Anything else funny shaped usually doesn't happen if the expectation is that it comes from the same distribution. Okay? Yes, there's always pathologic things that can happen, which is why I tell people to check. But generally speaking, I will show many examples as to the log normality of things that we ourselves have measured. Okay? So like I said, it tends to be a multiplicative thing that happens. So take a look at inhaled dose, right? Well, there's the time of exposure, there's the concentration at that time, there's the breathing rate, and then there's the fractional value of what goes in with respect to what comes out. These are all multiplicative. So if you were to take a bunch of people like you guys and measure the benzene in your breath, I'm going to get a log normal distribution. I'm not going to get a normal distribution. I'm not going to get a flat distribution. If I get anything, I'm going to get something that looks log normal. And yes, I could get a bimodal distribution if women and men were somehow different and were from different distributions. I could have different peaks. And that happens. But then you realize, I got to take a look at the metadata. When you get something that doesn't look log normal, it's time to look at the metadata. For the most part. I mean, it's much more likely to be right than not doing that. So, here's where the rubber hits the road. Suppose we've made a bunch of measurements in our lab, and we want to see how does this compare to the rest of the world, okay? Typically, when you read a journal article, you'll have summary statistics being presented to you, and you don't know what the original data look like. So, we often want to see in our own data how much is beyond a certain level of biological concern, how does the central tendency compare to other central tendencies, what's the fold range, what's the spreadiness of the data compared to other data, and then what is the actual central tendency. Typically we want to know the median value, okay? So, we have, from ourselves, a whole bunch of data, and you note we publish it with GM and geometric mean and geometric standard deviation, and you'll see in a little bit why. Once we have those two parameters, we can calculate all kinds of stuff. Okay? From raw data, we can calculate mean, standard deviation, CV, min, max, medium. We can do all that, right? And oftentimes people will not tell you all that information, and you have to infer it. So let's back up again to our own measurements. These are real measurements in pre-exposure samples from pavers and road workers and guys who slop around with the black stuff on the road. Sure, some of them will come in with a little bit extra exposure from the previous day, but this is this is pre-exposure information, hydroxypyrene, which is what we use as a surrogate for PAH's exposure. And you can see once again that the log normal model is better. Okay, it's real data. I mean, I didn't make this stuff up. You know, Sobis made it up. I didn't know. No, it's real data. Here's the post-exposure data. Okay, we're going to certainly have higher, lower. Okay, and again, log normally distributed. So, if we want to know, for example, anything below about 400 nanograms per liter is what we call a de minimis risk. we can go into that distribution and calculate that. Suppose we say, okay, well, anything above 4,000 maybe have a certain amount of risk for arterial inflammation, and say something over 14,000 maybe has 10 to the minus 4 cancer risk. Okay, these are all reasonable numbers, and you can get different numbers out of the literature. It really doesn't matter. This is a gee whiz kind of thing. So how would we do that? Well, you can write the equation, but this is really hard to do, and I haven't ever got it right on the first shot. Luckily, in Excel, you have the lognorm.dist function, which does all that for you. And so by using that function, we can now answer those questions with one keystroke, or two keystrokes, by knowing the geometric mean, the geometric standard deviation, and what x value we want. The lognorm.dist gives you the integration of the log normal model from 0 to x. So anything below 400 has an area of 0.238 in a standard normal distribution, a standard log normal distribution. Similarly, to get something above 4,000, you would have to go 1 minus that function because it always goes from 0 to x. The total area is 1. Subtract 1 from that, 1 minus that. So in this case, in this hypothetical scenario, you would get 13.5% above 4,000, and similarly, 1.8% above 14,000. So just by knowing the geometric mean and the geometric standard deviation, you can answer any hypothetical that somebody in the real biological risk assessment world would ask you. If you tried to do this with a normal distribution, all your answers would be wrong because the stuff isn't distributed that way. This is the cautionary tale. And so here's just the reprise of what I just said. You can answer the question by knowing two numbers of the distribution. Now, if you want to compare your stuff to somebody else's stuff, you got a problem. So just for fun, hydroxypyrine's been measured for 30 years, 20, 30 years. I went through the literature and I picked out papers that measured hydroxypyrene or other metabolites that included hydroxypyrene. And on the right-hand side, you see the statistics the paper gave me. One guy gives me mean and range. One guy gives me mean, median, 95th percentile. One guy actually gives me the GM and the GSD, but then he has left-censored data with percent LOD. And you can see that people publish different kinds of summary statistics that are convenient for them, but not so much for me. So if I want to do that exercise for hydroxypyrene I just showed you with this, I really don't know how. You know? I know now because I had to worry about this. So if I want to use other people, if I want to use other people's data, I'm going to have to make some assumptions. I'm going to have to assume that their true data was actually log normal. And this is not a bad assumption for the various reasons I've already presented, and the fact that when we did it ourselves, we got log normal. And what we'd like to know is the geometric mean, the geometric standard deviation, and another factor we'd like to know is the coefficient of variation, because that tells a little bit of a story in and of itself. So, back to how to do this in Excel. We can, with any list of data, if we get all the data, we can calculate the GM and the GSD just by logging the data, taking the mean and the standard deviation, which are the mu prime and the sigma prime, and going back into real space with the exponential. And that's the definition. If the thing is normally distributed in log space, this is how you calculate the geometric mean and the geometric standard deviation. Pretty straightforward. The CV is calculated by mu over sigma. Sigma over mu. And for now, this is just something I always calculate because I like it. But here I'll show you in the next slide why I like it. I can have different amounts of log normality in things. So if the CV is below 0.2, and in this, I made these data up. These are not real. When you use the true distribution, or the normal approximation, you get basically the same thing. So if somebody gives you a mean and a standard deviation, and you figure out the CV, you know right about where you're at. If it's below about 0.2, you can stop there. You don't have to go into log normal space to do your statistics, because it'll turn out pretty much the same way. If, however, it's around just under 1-ish, you start getting a spread, and then when it gets over 1, you definitely have to go into log normal space. Okay? Often, the first thing I look at is the CV, and if the CV is below 0.2, I know I don't have to worry about log space. This is why I calculated, because you don't want to make more work for yourself if you don't need to. So the question now is, if other people are publishing weird statistics that you want to use, how do you get to GM and GSD given odd summary statistics? Well, if I define, and you're going to leave this up for them, right? So I published this, so you can look it up if you care to. By defining my parameters, you always got to define them. By the way, every paper that worries about this uses different nomenclature, so you have to be real careful. This is the nomenclature I use, where I prime the mean and standard deviation in log normal space. Some people go the other way. You just have to be careful. Anyway, so that's just there for FYI. If somebody gives me the median and some percentile, 95th, 90th, whatever, I set the geometric mean to the median because that's essentially the definition of median. I can calculate the geometric standard deviation using that equation where the x sub c is the number of, say, the 95th percentile, and the z-score is the z-score of the 95th percentile, which in this case is 1.86, one-sided. And you can just calculate it. And it will spit out an estimate of the GSD by knowing the median and some percentile. Okay? Similarly, if somebody gives me the median and the range, it gets a little trickier. Here you have to make an assumption as to what the percentile of the biggest number is. Okay? This gets a little dicier, but if you set the max to being 1 over 1 minus n, so you have 100 measurements, and the max would then represent the 99th percentile, because if you did more, you might get another one past there. This is an assumption. It's not a bad one. It works reasonably well. And again, you do the same calculations in Excel, and you can get your GM, your GSD, and then you can get your coefficient of variation as well using that other equation, which I'm going to tell you how I got later. Ad infinitum, if they give you the quartiles, you have an equation for that. If they give you the mean, the mu, and a percentile, it gets a little trickier, but it is possible to, with these equations, convert a summary statistic of any sort back to a GM and a GSD and a CV. The one that was the trickiest for me was this one, which is somebody gives you the mean and the standard deviation of the wrong model. Okay? So now you got to convert two things. Usually if they give you the median, at least one part of your job's done. But if they give you this, you literally have to do some homework, and I've done it for you. So what I want to show you here is, again, the value of the CV in all this. If you plot mu over GM, so mu being the mean, GM being the median, versus CV, you can see that, he says, the early part is pretty flat. This is what I showed you before. The distribution of log normal and normal are pretty similar as long as the CV is below 0.2. Okay? The GSD is a little trickier. I spent a lot of time and effort on this graph because the literature equation is for perfect data, and I had to modify perfect data for the increased scatter you get, because your approximations get worse and worse and worse as the CV gets bigger and bigger and bigger. So once you get up over 1, no matter how many times you do it, you get, with real data, with real error in it, 2 minutes? Oh, I'm not even close to done. Anyway, here it says 42. All right. Where was I? Now you interrupted me. Okay, so how well does this work? Okay, well, taking the same data set, calculating the different parameters, I can recreate the GM and the GSD, and I get pretty much the same result each time from a real data set where I have literally taken the data and made for myself different summary statistics and then back calculated. So I know what the truth is, and I know, and you can see it works pretty well. And if you blow this up and say we go back to the example greater than 4,000, we can see that we get a pretty good estimate of that risk factor. And in fact, the area, which we expect to be 0.13, we can estimate at 0.09, 0.06, 0.1, 0.1. Okay, this is from real data with real scatter, so it's really not a bad approximation. So, bottom line, we can do this. And now the next question is, how does this have value for doing things with NHANES? Well, NHANES gives us lots of summary data, and they give us good summary data. So how do we compare the disparate measures? Okay. We're back to this. This is what we want to accomplish. What does reality look like with respect to toxicity? And given all the stuff I've told you, where I know what the accurate number is from the NHANES data, because they give me every single number, I can now take all those other papers, use that technique for all the different summary statistics. I can now approximate the distributions from something like controlled workers in Ghana with respect to Poland coke oven workers, with respect to Finland soil digging occupational exposure. So now I can take all of this data that's out there in the real world, satisfy EPA's critics by using other people's data, and actually put things into context. Pretty cool, huh? So Jane says I got to quit. All right, so I have a bunch of stuff. This was just the mathy part. The one thing that we're really working on is the AOP, the Adverse Outcome Pathway. And so we have this tiered approach where we want to go from people down to molecular level, okay? So we really want to be able to link across. Sure, you can do faster studies at the molecular level than at the people level, and then the cellular level is kind of in between. But this is how we're looking at it. Here's how we look at it from the exposure assessment plane, where we know what the exposure is, we know that we can measure some things, but we want to map forward to the perturbations. Okay? So in this case, we can measure that axis and that axis, and we kind of have to infer that one. So with respect to this is just another plane that we insert. And so how do we do that? Well, what we really want to do is go from the environment to the people and from the measurement of the biomarker to the people. And the first step here is taking blood, breath, and urine samples, running some broad discovery thing on them, and saying, holy cow, look at all these peaks we got. And this is the discovery side. And from there, we can start interpreting things. However, by measuring a lot of things at the same time, we don't do a good job in any one of them. So we can go the other direction, which is what we call the targeted approach. And we start off by looking at specific things and ignoring other things. And now you can see you get much better chromatography in this case. And this is a very simple GC mass spec kind of trace. And if you compare, for example, the benzene peak out of going targeted with respect to the benzene peak from going discovery, you see an advantage of being targeted, but you notice you miss a lot of stuff. Okay? Again, there's no such thing as a free lunch. So for discovery analysis, we need a pretty much high-end instrumentation to do a good job. Typically, high mass resolution mass spec. I guess that's the best example. And for targeted, we can go very specific and we use lower tier instrumentation. So I've been working on this now for a while, and there's a series of different projects, and the one that I kind of like was what I did with the folks at Pisa, where we took a look at liver function and anesthetic exposure. This was fortuitous in that we had a bunch of guys undergoing surgery, and we had the opportunity to measure their exhaled breath, both for sevoflurane, which is the anesthetic that was being used for invasive surgery, and also the one of the metabolites produced only in the liver called hexafluoroisopropanol. So, as an overview, we built a little conceptual PK model where we have the administered dose. We can measure the we interpret the sevoflurane in the blood. We can measure it in the breath. The dotted thing is the breath. We also know that it gets distributed, and we know that it gets metabolized to HFIP, which we can measure in the breath. Okay? So all this other stuff happens without us really having to deal with it. We can write the equations for all that, and now we can build a model that we take the data and we interpret the model, and we can basically model the exhalation of sevoflurane with the only parameter being what the administered dose was. If we go into the HFIP model, we see that from the and the models were built from the literature, not from the actual data. We can see that we match the data of 4 of the 6 subjects really well, and that the other 2 are wacky. Well, this bothered me to great end because I thought, oh my God, my model doesn't work. And I only had 6 people to deal with because these guys were getting bowel resections and all kinds of horrible things. And anyway, it wasn't like you're going to do a lot of them. But it turned out I could fix my model to fit the data only by putting in a time delay. The only parameter I changed from the original model was to put in a time delay. Why did that work? Well, apparently when they do surgery on people that's messy, they sometimes shunt the liver blood flow because they don't want to get all that junk that they're putting into the bloodstream to be stuck in the liver. So they shunt the liver blood during the surgery, which means the liver's not metabolizing anything because it's never seeing it. And so I said, this might be useful to diagnose whether or not the liver's actually working. And they're now embracing this concept, and they're going to start doing this to see on liver transplantation when the liver starts actually working again without having to do biopsies. Pretty cool, huh? Simple breath measurement. And this was now pushed forward to toxicity testing, and we're doing this right now. They're doing this while I'm talking to you. But the idea now is use something like sevoflurane as a probe molecule for liver function. Except now put the liver cells in a bucket, tease them with sevoflurane, measure how much HFIP they're making, and then throw in some fairy dust that may or may not be toxic and see if it messes up liver metabolism. It's a very elegant way to do a longitudinal test on different compounds instead of the parallel tests that we're now doing primarily for various liquid-borne biomarkers. And in this case, you only have to measure one thing. You measure the metabolite. And the analytical signal is how much or how little of the metabolite you got. Okay? So, like I said, I'm running out of time. But I do have conclusions and implications. So one of the things we're going to start doing is instead of looking for individual compounds for individual AOPs, is to try to see if we can just tease out various cellular function, different CYP pathways, just by setting up a steady state of a probe molecule and just measuring the metabolite. And if the metabolite goes away, then you have this idea that that pathway has been disrupted, and that is an indication of toxicity. It can be done pretty quickly. Okay? That's what we call the probe molecule thing. Keep your eye out for that. We published one paper on the hypotheticals, and we are now working on the implementation and the data. So, okay, sorry about that. I rambled on, so I will quit now.
Thank you very much.
And if Jane lets me, I'll answer questions. Yeah.
Do you ever have to work with the correlation among those variables? I think the fact that the correlation coefficient for log normal variables isn't the same as it can't just be directly radically translated.
Okay, what kind of correlation are you talking about? You like linear regression or mixed model correlation or what?
You're looking at maybe two variables, like whether there's a correlation in effect size.
Okay. Yeah, I can answer that.
Different effects from one exposure.
Yeah, I can answer that.
Variables that you're looking at that you translated from a log normal to a log normal.
Yeah. So if you are log normally distributed in your original data, you go into you log the data and go into, which is now normal space, but it's log normally transformed space. Okay? And now you can do your linear regressions, your R-squareds and everything. And those R-squareds are actually accurate because they require the assumption of heterogeneic variance, which you don't have in a log normal distribution. So you do your statistics in the transformed space. And those statistics are robust. You don't go back and try to do it. In fact, a lot of times when you have to plot the data back in real space, it gets a little messy doing a linear regression plot because it turns into a curve. So this is the case where I go with a log scale and I recalculate the equation for the regression and I overlay it in log scale. So you go y equals mx plus b, but then you do log y equals m log x plus b, and you can back calculate it. So I agree with you. Yes, it is very tricky, especially when you have to explain it to bosses and such. You really have to kind of cheat to get a straight line, but plotting in normal space. And the way to do that is to write the equation a different way.
Not getting into detail so much. My question had more to do with whether you have, I guess the variables you're talking about, are often represented with the implicit assumption that they're maybe normally distributed, at least that's what you're implying, so that they might report correlation coefficients, like Pearson correlation.
You're talking about other people's data?
Yeah.
Okay, so there's a caveat with that. You have to assume they did it right. Right.
Are you ever interested in trying to do some kind of meta-analysis on correlation coefficients across data?
Well, that would be something I have to do in hypothetical space, and we haven't done that, but it's a good point. But again, the biggest caveat I have, if you use other people's summary statistics, the first thing you have to assume they actually did it right. And what I've seen is when they provide the 95th percentile or whatever, they've modeled it instead of measured it. And now, what does it mean? If they use the wrong model, it's the wrong tail, right? The way I do it when I do a 95th percentile, I'll line up all my data, and I use a little equation down at the bottom, and Excel tells me which the 95th percentile is. There's a little, or you can just line them up and count until you get to the 95th percent. So if 100 data points, it's the 95th one, it's the 95th percentile if you order them, right? That is, the biggest caveat is not this little bit of fooling around with the distributions. It's, did those guys even do it right in the first place? And I got nothing for you there. You make that assumption that when somebody publishes it, they actually mean it. You already asked the question. Well, give,
So if you're combining data sets, do you correct it for multiple testing? Like, are you doing any
no, that's all independent. That's all independent. I mean, if a guy did something in 1903, it's going to be independent of... No, I don't have to combine anything there. She's talking about test-retest statistics, Monferroni correction, or Tukey, or whatever. No, you don't have to do that. I mean, they're completely independent estimates. But you don't have to do that.
Any other questions?
Well, he had a question, but I shut him up. Huh? Sorry about that.
I guess this might be, I appreciate the org chart's really big, so this might be not in your star location, but I was just wondering, there's lots of chemicals we're exposed to in the environment. How do you tell that it's the one particular one that's making you sick?
You don't. This is why we have gone from the one chemical, one health effect model to the discovery approach. And There's no easy answer to this. The biggest thing that we're doing now is trying to address mixtures. And our addressing of mixtures starts with not 6,000 chemicals, but it starts with 10 of similar congener construction or whatever. And we're doing a lot of work with QSAR, quality, structure, activity relationships. It's not easy, but you have to understand that the only way you're ever going to get a handle or get traction on mixtures is systemically, and probably not with the in vitro tests, which we're so enamored with right now. So there has to be some of each being done. Basically everything I do is with mixtures. I mean, we're mixing diesel exhaust and ozone and then making a measurement of pulmonary function and cytokine response. And we almost don't care what individual chemical does anything, because you're never exposed to one anyway. If you're standing out by the bus stop, hey, it's diesel.